Alright, hey everyone. We're going to be doing a tier list of all the electromagnetic formulas so I can remember them and so I can choose which ones to remember, more importantly. Alright, so we've got the whole list here. There's a fucking lot of them. But we'll just go... I've sort of tried to randomize them a bit. I don't want them to do in a row because they're from very different categories. For most of them, I'll try and show part of the PowerPoint presentation on the slides about it so you can get a clear understanding. But we'll start with this one. This is the equation for, it's to do with resistance and it's to do with the velocity of a charge. This tau symbol there, that represents the average collision sign. So that's, it doesn't just immediately accelerate if it's in an electric field, a particle. The tau symbol represents that. And you don't really tend to use it, but it is handy for understanding that there's some sort of thing that slows down how fast a charge moves. So we'll put it in B tier, I suppose. If you never use it, we'll put it in C tier. This one here, this is just it's kind of interesting. It tells you, it brings you from the electric field, which everyone knows and loves, into the electric flux density or electric displacement, as I like to think about it. So it's kind of useful, but it's also kind of boring. It's just a conversion. I think we've got a few more conversions. I'll just get rid of them real quick. This is the equivalent for magnetic field. So H is the magnetic field that we like. The B is the magnetic flux density, and that's got the permeability constant, I think, which is dependent on the material. For this one, it's dependent on epsilon. Actually, we'll bring them down to B. Really, they belong in B. B for magnetic flux density. Okay, moving on to this one. This just tells you what conductivity is, which is the inverse of resistance. It's dependent on a bunch of things. It's dependent on the velocity, it's dependent on the mass, dependent on the number of particles and the average number of collisions. You can get it back down to 3 terms with this one. This is just a replacement for Q tau on M. M's mass. These are both just explainers, really. They don't really have any proper purpose. This one, I'm not going to put an SS, but it's pretty important, so we'll put it up here. This is just for you to calculate the resistance for a non-round shape. I've got the round shape version here, which is a lot easier, but this shows up in all kinds of exams. This is a fair bit easier, but because it's so easy, it probably won't show up in exams. But that just tells you how to find the resistance, giving a bunch of geometries. It's all dependent on the area. So this is just for a non-linear area. And the permittivity. Really, it's just 1 over permittivity. That's what R is, but you need to take into account the area, of course, as well. This one is the how long it takes for electrons to sort of bounce around. I'll just get up the slide that tells me about that. That is to do with conductors, I believe. Here it is. So how quickly charge can be redistributed, which is important for things like the skin frequency. It just tells you that you need copper, basically, if you want to use any high-speed connections or data processing, whatever. It's pretty important. I think we're judging them harshly, so we'll go TCR is there. And next to it, we've got the bandwidth 1 for that, which is it just tells you how high you can go if you've got a time constant, which is the permittivity over the conductivity. It's all related to magnetic fields and the conductivity, which is electric fields. And its companion is BCR, which is here it is. You can see this is in hertz because it's got the over 2 pi. I'll get this out of the way. This is important in other subjects, not really important in here. It's just mainly used as a teaching device. So even though it literally constitutes everything you do as an electrical engineer, I'm going to put it in C tier because for electromagnetics, it's not really that important. I'm going to get a lot of hate for that one. This one is just relating. It's kind of the same thing. So this is like the form we know. This is also the form we know, but this is just relating the current density, which will use tons. It's basically the point form of the current. So this is just relating it back to circuit theory, which uses these ones, but we're looking at field theory and electromagnetic theory. So we are more interested in J. So this is just conversion back into the traditional way we look at circuits. This was very important. This relates Coulomb's law to the electric field, which is basically used everywhere. So yeah, we'll put it in S. I might change that later. But yeah, that's really important. It just basically tells you what an electric field is. It's Coulomb's law divided by a charge, so you don't have to worry about a single charge. I think I got a video on that if you're keen. Yeah, this just tells you what current density is. Not really that important. It's kind of like this one. It's just like, sure, the current density is to do with the density the density of electrons times the number of electrons times their velocity. Pretty intuitive, but sometimes useful for examining things, but you're certainly unlikely to use that in an exam. Skin depth, this belongs straight to S tier. That's very, very important. So the skin depth, the length into the skin, let's see if I can get the diagram. I think it actually is on the bottom of that one. Skin depth. So that's the skin depth there. You want to calculate how much that is, which you really need to, because it completely is dependent on, the resistance is completely dependent on that. It's this one here, so the angular frequency, so it depends on frequency. So as the frequency goes up, skin depth happens, of course, that's the whole point of skin depth. And then it's to do with the magnetic field, which is represented by the permeability, and also, of course, it matters if you're using ceramic or copper. So we've got the conductivity there as well. So that's S tier. I don't even know if we're going to get it SS. Surely when we get to Maxwell's equations. This one's pretty important. My brother showed me a question from his first year physics course, and I didn't know how to do it because I forgot about this equation. So we'll put it up to B tier because sometimes you do need to know. It just relates Coulomb's law for a single point charge. That's what the radius part is for, and it's pretty useful sometimes. You can say that it depends on the charge, which is why you got a Q there. Alternatively, this could just be an E and it'd be KQ over R squared, but you can forget the Q because, of course, F equals QE, so that's in S tier. But yeah, that's pretty important as well. This is just a regular old physics one, but it's useful for explaining. I suppose we'll use the useful for explaining ones here. This is conservation of charge. Basically means if you got charge coming out of a surface, that's equal. So if you got current coming out, and current of course is dependent on charge per time. So that current going out over an area, which is J dot dA, is equal to the amount of charge coming out. It's negative because it's charge has to go out in order to form a current if you're talking about dot dA. I suppose this is pretty important. We'll put it in B tier. We're being picky. This is just, I try to mix them up, but this is just the point form of that. It's a lot more elegant though. It makes a lot more sense when you look at it. But it's not worth A tier. Put it there. C equals dQdV, it's a classic. You probably need to know this to get your head around pretty much everything. So we'll say A tier? Yeah, we'll put A tier. Capacitance is the amount of charge that goes out per voltage you put across it. Of course, that depends on other things as well. I mean, the capacitance is the culmination of all those things. I'm sure there's a whole thing that gives you how you get that capacitance. Yeah, in fact, let's find one. Here we go. Capacitance per parallel wires. Capacitance in parallel wires per unit length. That's what that hat's for. You'll see that crop up a couple times. That is, yeah, the capacitance between them. Obviously, it depends on epsilon, which is the permeability. Yeah, we'll go C. Oh, B. I mean, yeah, B will do. Oh yeah, well there's one right here, parallel plates, that's the same thing. We'll put all these next to each other so you can easily look at them. In fact, the best way to do it is how my tutor did it, which was you line them all up. Not tutor, professor. Do this for all these equations that be coming through. You just watch. Here it is. Here we go. So for parallel plates, that's like a really old style capacitor. That's really cool. Always think about that. That's the easiest one. Then you got coaxial cables, which are kind of a pain, and then wire pairs, which is even more of a pain, but that's the one you use all the time, I suppose. Pretty sure the wire pair actually relates to round wires, which I'm not really sure how that would work on a PCB. I suppose you could approximate them. Here we go, here's the parallel wire thing. That equation, I think that'll go like F tier. But yeah, so it's for two round wires, because it's dependent on the radius A, which is here. And I don't know how round PCB traces are, but whatever. Oh, they are. I don't know. Yeah, that's one of them. Fuck it, we'll put this FD. I don't know if I'm ever going to use that. Capacitance per unit length. I suppose it's up here as well. So those three belong together, as you saw in this one. Which one's a coaxial one? That one. That one's. No, so that's actually wrong. That's supposed to be coaxial. Whoops. And that's supposed to be parallel wires. Now we've got the voltage. The voltage is related. This is for capacitance stuff as well. I think it's coaxial. Yeah, coaxial. So we'll put that also F tier. I mean, I don't know, it might eat my words in a few practice exams time. This one has to be SS tier. That's Ohm's law in point form, which is the foundation of everything to do with charge. So the current density is equal to the conductivity times the electric field. So if you put an electric field in conductivity, which was like a squillion, let's see if I can find that. Conductivity varies. Well, I could tell you that the conductivity for copper is like 10 to the 9. Well, this is what we're talking about. But the conductivity for copper is like a squillion. So if you put like the tiniest electric field, you get a ton of current. And that's why we need resistors, because if you put a battery with a short circuit, it's just going to flare up and start a fire. So that tells you why so much current comes from so little conductivity in things like copper. Obviously there's none in insulators, but still. Okay, we'll look at this one. This is to do with wires. Now, there's a lot of really annoying wire parts here. A lot of annoying wire equations. In fact, I'll show you the wire impedance. It's a shocker. I didn't even do the second one, I just did the first one. This one here, impedance of a finite length wire. And that is this one here. That's going F tier. Because it's got rho is annoying as it is. It's it's R hat plus SL hat. It's all in the Laplace domain. And then you've got this one is here, which I don't even know how to handle. They haven't put a box around this, so presumably it's not that important. If I get a question like this in the exam, I don't know how I would handle it. Probably take me like half an hour to do a basic calculation. But anyway, so let's just ignore that. This one's pretty good. This is the flux out, is the magnetic flux out, sorry. And that just equals the magnetic flux density out of the area. Pretty self-explanatory, but it's useful-ish. I don't know, I just think it looks neat. It's very, well, it's neat. It's very, very neat. Let's make this a bit bigger. So that's how it's looking at the moment. Okay. Oh yeah, this has to go right next to the skin depth one, because this is all to do with the resistance of something with a skin depth of something given by the equation up here somewhere. That one there. Well, I want to put that in S tier actually. The skin depth one. We'll put it in B tier. How's that? I mean, it belongs with that one, but it's not as important. That's pretty self-explanatory, really. Where's the... Yeah, so it goes from that just to that. It just tells you that all you care about for resistance is this little bit. Obviously, the resistance is much higher because if you have more area, you have less resistance. That's why ground planes are so good, because there's so much area. No resistance just flies back to the ground, so there's no interference, unless there is, which is one of these equations. Here we go. This is all about this is another wire one. Yeah, it's all about the ground bounce, because if you have a bad ground plane, sometimes a certain ground voltage will be different to another ground voltage. Pain. I hate these wire equations. It goes D. Probably it'll be useful, but I don't want it to be useful. This is the inductance, I'm pretty sure. No, the wire impedance. Oh, whatever, we'll just put it in F tier. This will go in F tier. This will go in F tier because I hate them. This will also go in F tier. This one here. These are all... maybe I'll have to make a video on that so I can make sure I understand it, but I don't want to do it now. Oh, this one's kind of interesting. That's to do with wires, I'm pretty sure. It's like the a wire over a ground plane. That would be pretty important. How much inductance there is between the wire and the ground plane. Is it in this one or is it in the other wire one? Oh yeah, crosstalk. But that's not what I wanted, I don't think. Whatever, I can tell you now. This is the inductance over a ground plane. This one here. Which is good, so I'll put it in C because that'll be the best of the really annoying wire ones. Let's do something a bit more fun. Here we go. This one will go A tier because that's really important. The gradient of the voltage is equal to the electric field, you use that a lot. It has a cousin, which is the voltage. It's like a line thing. Yeah, here we go. This is the line integral. So if you trace a line integral with the particle, it tells you how much work is required to push it up to a certain place per charge, and that's voltage. So that's its cousin, but we're going to put that in B tier. I suppose we'll use that tons. A lot of these are just how much I like them because they're simpler and easy to understand, as opposed to how much they're actually used in an exam. That's what I was aiming for. But this one's great. Del V equals E, because it tells you that the gradient of the voltage. So if you're imagining voltage as part of a hill, like I put in one of my videos, if you imagine voltage as the height up, then the gradient of the hill is equal to the electric field. So how quickly the voltage drops, that's obviously, if there's a very high drop in voltage, there's going to be a high amount of electric field there. And there's some really good diagrams, but there's none on the slides. Let's see if I can do voltage gradient field MATLAB 3D plane. Voltage gradient electric field. Yeah, okay, this is kind of cool. So this is the electric field. So the voltage would be the gradient of this field, how quickly it's dropping. So how fast those contour lines are going together. It's good. It's interesting. So we'll put that in A tier. And then this is kind of cool. This is the ringing frequency. So there's a nice little diagram of what happens when you've got a ringing frequency. It just has a full version of the RLC circuit that oscillates, which is the underdamped. Here it is. How cool is that? So a little pulse will turn into a big oscillation, like in underdamped. Where was it? If ring, yeah. That's pretty important. We'll put that, and also easy to understand, hence why I like it. We'll put that A tier, why not? And the other cool one's the knee one, the knee frequency, that tells you, put A tier. That one tells you if your time to go up is faster than, if the signal you're trying to put through a wire is faster than the switching time, which is how long it takes to go up, then you're not going to have a good time. It's going to be shocking. Where's the... No, it's not this one. Knee frequency. That's the ringing frequency. And the reason it's called a knee is very intuitive. Here we go. So it's the knee part of this goes down at 40 decibels a decade. And yeah, so this is the T rise and fall, which is equal to T switch. We approximate them as equal. So if your frequency is faster, like than here, if you're trying to switch up like quicker than it can rise and fall, it's only going to get like halfway, and it's going to be so distorted, it's ridiculous. So that's why you get all this horrible noise here, and that happens at the knee frequency. So you obviously don't want to do it there. This is what happens at the clock frequency, and that's bad enough. That's when the signal you're trying to put through the wire is the frequency is equal to this bit. You get a bunch of harmonics, but you do not want the signal to try and go up and down quicker than it can actually rise and fall. It's just ridiculous. So that's your knee, and it's also intuitive. I like how it's intuitive. Length. So you don't, actually, I suppose we'll just go over D real quick. That's what a regular rise and fall of a USB signal would look like. Just kind of dodgy. That's all the noise you get from it. How many D was in this one? Propagation delay, that's it. So that's how quickly it takes to... There's a cool bit here. It's like if you times the inductance and the capacitance together, so which tells you how quickly it's going to rearrange. It always is a product of the permeability, magnetic permeability, and the permittivity, which is interesting because both of them are related to capacitance and inductance, of course. That's just the velocity, it's just 1 over that. But how quickly the signal can rearrange within a magnetic and electrical pathway is given by these two values, which tell you about what kind of material you're using. And this delay will tell you how quickly you can switch something. Well, yeah, so it's given by the root LC, which is also equal to the root of the permeability times the permittivity. And we'll put that beta. This is just like, this just means that you don't want to use all those decimal places. You want something a bit neater. You don't want times 10 to the negative a million. So it's just this one, which is the base. That's a base in free space. That's that permeativity times the permeability, and then you use references to that. So there's a nice table which explains how that works. Yeah, so it's relative to the free wire space. So instead of saying FR4 equals 2.5 times 8.854 times 10 to the negative 12 farads per meter, you can just say it equals 2.5 times the permeability of free space, which is a lot easier to say. So I don't know, that's kind of easy. We'll put it in C because it's not really that necessary. This is one of Maxwell's equations actually, but it's easily the worst one of Maxwell's equations. Because it just says that there's no such thing as a monopole magnet. There's always a second part of it, so even if you break a magnet in two, it's still going to have a north and south pole. Look, it's still a Maxwell's equation, so we'll put it highish up. The sin to put a Maxwell in B? Nah, fuck it. You'll never use it. It's just like, just for proof of concept really. It's like a footnote. Where did the other Maxwell's equations? Well, we got them in point form and we got them in integral form. Oh, don't tell me I didn't put... Oh man, I don't think I even got... Where's Gauss's law? Oh, that's so bad. I'll just get it up for you. Gauss's law in integral form, because the integral form is way better. Yeah. This one here. So the flux out of an area is equal to the charge inside. One of my textbooks was just in love with Gauss for the fact that he figured that out. I mean, it's pretty impressive. It's like all the electric parts of the field that come out of a certain area is equal to a charge inside it. I mean, I don't really know how to say it better, but it's and you use that all the time. If that would be in SS tier, I can't believe I don't have it here. It's ridiculous. Maybe at the point form. No, not even. Okay, whatever. Surely okay. This is another one of Maxwell's equations. This one's pretty important. So we'll put it in SS tier because it's Maxwell's, and it's not boring like this one. 0 equals, yeah. This one relates, I think this is Ampere's law, and it tells you that the magnetic flux out is dependent on the current, which is obviously very important. Current induces a magnetic field and vice versa. But also this bit here, which is the displacement current, which the reason it's added on is because there's obviously no current in a capacitor, but it still has a magnetic field around it, but only when it's changing. So if you put a changing electric field through a capacitor, aka the only thing you can put through a capacitor because it blocks DC current, you can also get a magnetic field. So this part's just to say capacitors actually do work too as well. They're a thing. But yeah, this one's massive. I don't think I even have it in integral form, which sucks. I think I'm out of integrals. This one's interesting. That's another one of Maxwell's equations. We'll put it in S tier because you still don't use it that much. But this tells you that an electric field can induce a change. Sorry, the gradient of the electric field can induce a time changing magnetic field, but rather the better way to put that is that if you vary a magnetic field, aka how a generator works, if you put a magnet inside and outside of a solenoid or I don't know, something metallic, if you change the magnetic field a lot, you get a current, you get an electric field basically, which is how it all starts. So changing electric field equals changing magnetic field equals an electric field. This one's interesting-ish. That's just ground stuff. I'm sure this will all be very important in high-speed design, but I'm not really looking forward to it. We'll put it in D because it's at least easier to look at. Just tells you that the inductance between a wire and ground is given by a few things. Yeah, wires. This one's interesting. This is a charge redistribution model. It tells you that the time rate of the charge is equal to charge per time is equal. Negative charge going out per second is dependent on the conductivity and the permittivity. Obviously, times the charge because it depends on the charge in the place. But this is just another thing that tells you that the material matters. When charge is coming out, it's dependent on the permeability and permittivity, like pretty much everything else. We'll put it at the top of B tier, because it is pretty important. This one confuses me, but it's important. It just tells you what the magnetic flux is and how it relates to voltage. I suppose I need to remember this one, so we'll put it in A tier. So it's the voltage is dependent on the variance of the magnetic flux, which I suppose is pretty similar to this Maxwell's equation that just tells you the electric field is related to the magnetic flux. So these sort of go hand in hand. Capacitance, this is a conversion thing, which is handy. The capacitance per unit length is equal to, obviously depends on the change of voltage, but it is also dependent on the charge per length. It's not really that important, we'll put it in D tier. This one here, this is inductance. This is all to do with, I did say that we would go over this real quick. I definitely had it, I remember. Oh, this is a great one. This one here. This is probably haven't gone over this yet. This is how you make a transformer, which is really interesting. It tells you how how you get inductance from a solenoid, which you can then use via this equation. This one here. So magnetic field is tied to the electric field to get a transformer, which is used in microphones, and it's basically something of black magic because no one really knows how to make it good. Apparently the transformers they use in microphones, especially back before we had semiconductors that you could use in audio circuits, the transformers were they have to take into account the regulations and the laws that govern which chemicals you could use when they're trying to make it a good transformer. It's basically alchemy. Oh, this is what I was going for before. But we'll put this one. I just like this one. It tells you that if you're trying to make a transformer, it depends on the number of turns you have. Its inductance, which is what you want for a transformer, depends on the number of turns you have and the area, obviously, and it depends on what material you use inside the solenoid. So this will go in 8 tier because I just like it, and it's related to music stuff, which is why I like it. So this is the equivalent of the capacitor thing. I also have the same. So 3 different things, 3 different ways to calculate its capacitance per meter or per area, etc. So this is the same thing for a coil. That's obviously pretty important. I wonder if I've got it here. Maybe I've already put it in. Maybe not. The inductance for a coaxial cable, I suppose that's important, but it's also pretty niche. We'll put it in C tier. And then the inductance for, is that coaxial? 2H. Yeah, inductance for parallel wires. This is pretty important. I'll put that in B tier, I suppose. IC equals CD, VDT. I'm going to put it 1 above Ohm's law. I was thinking about this before I started, because it is still important for if you're talking about voltage and current. But I guess this is obviously a general use thing that you use all the time in more basic electronic circuit theory applications, but it's still useful for point form electromagnetics, so we'll put it in B tier. We'll put this next to it because it's the companion for inductors. The length, yeah. Oh, that's what I was going to do before. So the if you're making a wire, and we had D, remember, which was dependent on the permittivity and the permeability. You want to make sure your wire is not shorter than this distance that we've calculated through that. Whatever D stands for, I can't remember. So we'll put this next to that one. T switch. Where do we put T switch? Where do we put T switch? Whatever. There's so many fucking formulas. So how will it? Yeah, B tier. That makes sense. Most of them are useful. There's only a handful in F, C, and D. To be fair, these ones probably don't really belong there. It's just because I don't really understand how they work. And we'll get this one, which is the this one's like the magnetic field produced by a point charge, I'm pretty sure, or sorry, a current through a wire. This one's actually pretty important because it's kind of a companion to Ampere's law up here. It's not going to go in SS. We'll put it in A tier because it says that the magnetic field introduced by a current, and it doesn't have that annoying J term, which you do have to use because it's in point form, but I'm doing a lot of contradictions here, but it tells you that a current introduces a magnetic field radially, and obviously it depends on R. It's kind of like the equivalent to the electric field with the charge, which was one of the first ones we did. This one here, it's kind of close to that one. Well, I really should have done this as electric field and just scrapped this cube. But I mean, I explained it, so I suppose it's not that bad. And we're going to finally finish with a few semiconductor equations. This one's talking about, I'll have to show what this means. This semiconductor equation relates the amount of doped positive parts and doped negative parts to the charge. The ND and NA are usually completely irrelevant because it's just a normal chunk of silicon that hasn't been doped. I mean, it's still a semiconductor that's quite used, but it's way more useful. I think this is about 10 to the 10, and this is about 10 to the 15. So this is 5 orders of magnitude greater than that. So anytime you have these together, the only time these are relevant is if N and P aren't part of it. But this is still interesting. It tells you how you get charge from a semiconductor. So we'll put it in B tier. It's really pixelated for some reason. And this is also pretty neat. This tells you the rearrangement time for... Let's get the semiconductor stuff up. That's the chunk of silicon I was talking about. That's the doped one, which is way better. The time constant. It looks like an RC circuit a lot, which is really interesting. Yeah, here we go. So the time constant for something to rearrange, aka the recombination lifetime, is what's dependent on how much you start with, of course, and it's dependent on what you end up with, which is n hat, which we've put as part of this equation here, yeah, it's dependent on this time constant. That's the main thing. So if I get the RC circuit equation, it's going to be like VF or something. I might have typed it in. Yeah, here we go. So that you can see the similarities between this one here and this one here. Should really say V0. Where's the one with V0? Yeah, that's better. Is it? Whatever. I'm presuming you already know this is an RC circuit. This is like first year analysis. If you don't know first year electrical analysis, this is a bad video to watch. But it's interesting. It relates a time constant. Gets you a time constant for something that you wouldn't think is at all related to resistance and capacitance, which is easily done with a symbolic, like, you know, if you're talking about something symbolic, you don't talk about a semiconductor. But we'll put it in A tier just because I'm feeling generous at the end of this video, and that's all of it. So let's get a whole, maybe I can make this smaller. There we go. There's your whole tier list. I still can't believe I don't have Maxwell's equations in integral form. I just have a few point form versions. Especially, let me show you my favorites. Gauss's law in integral form, that would be S tier. Ampere's law, that would also be S tier. Faraday's law, whatever, that'd probably be B tier. No, maybe not B tier. Be the same, because it's the equivalent of, where's it in point form? This one. Maybe I would put in S tier. That's boring. This one's very, very interesting. Let's just get Maxwell's equations up. can look at their beauty. No, I don't. Yeah, that's better. I prefer the electric flux density to the electric field with the constant. Boring. Interesting-ish. S tier. That one there. That one's really elegant. Just it tells you that at any given point, if you take the divergence at that point, so is it a source or is it a sink, that tells you what the charge density is at that specific point, and that's really elegant. I like that even more than the triple integral, especially because it's a lot easier to calculate as well. It's 3 less integrals you have to evaluate. So this is the mostly complete up until week 9, but obviously there's a lot more to come, and hopefully the semiconductor ones aren't as annoying as the wire equations, which we have all done here. But yeah, so that's it. I'll update this in 3 weeks.